Welcome back to our ongoing deep dive series on the OEIS.
Great to be here.
Today we're jumping into sequence A000231. For our regular listeners, especially those number theory students tuning in, the OEIS is just, well, full of gems.
Absolutely. It's an incredible resource.
And this sequence, A000231, and might seem like it comes from logic or computer science initially, but I think we'll find some interesting overlaps with number theory thinking.
Definitely. I mean, number theory thrives on patterns and structure, right?
Right.
And the OEIS is pure panel.
Exactly.
Even sequences from, say, Boolean algebra, like this one, they can shed light on core mathematical ideas, things like counting and symmetry. A000231 is a perfect example.
Okay, let's get into it then. What the definition is, the number of inequivalent Boolean functions of non-variables under the action of the complementing group.
Right.
Quite a mouthful. Let's unpack that. Maybe start with Boolean function of non-variables. What are we talking about there?
Yeah, good place to start. So, simply put, it's a function that takes no inputs. Each input has to be binary, so either 0 or 1.
Okay, binary inputs.
And it spits out a single binary output, again, 0 or 1. So it maps, mathematically from the set dole that's the tables of zeros and ones to just dollar.
Got it. These are super fundamental in, digital circuits, right? Computer logic.
Exactly, they're bedrock. They represent how computers manipulate binary information. Think about the simplest case, one-out OP. You have functions like identity, where the output matches the input, or negation, where the output is the opposite.
Okay, basic building blocks. Now, this next part, the complementing group action, that sounds a bit more involved.
It is where the notion of equivalence comes in. It defines when we consider two different Boolean functions to be, well, fundamentally the same.
How so? What does the group do?
All right, so two functions are equivalent under this group action if you can get from one to the other using two kinds of operations. First, you can pick any subset of the input variables. Could be none, could be all, could be just some. And you flip their values. You change the zeros to ones and the ones to zeros just for those selected inputs.
Complementing the inputs.
Precisely. And second, you have the option of flipping the entire output of the function. So wherever it was 0, it becomes 1 and vice versa.
Okay. So input flips and maybe an output flip.
Exactly. The complementing group is just the set of all possible combinations of doing those input flips and the potential output flip. It represents basic symmetries negating inputs, negating the result.
So if I have one function and I mess with it by flipping some inputs, maybe flip the output too, and I end up with another function, they're basically considered the same type.
That's the idea. They fall into the same equivalence class.
And A00231 is counting the inequivalent ones, the distinct classes. Why filter it down like that? Why is that important?
Well, think about it. For non-it variables, the total number of Boolean functions is $2 raised to the power of $2.
Whoa, okay, that gets huge really fast.
Incredibly fast. But a lot of those functions, they start to look very similar if you allow for these complementations. They're not fundamentally different in their logical structure.
Right.
By counting the inequivalent functions, the number of classes, we're trying to get a handle on the truly distinct types of logical behavior.
Right.
We're boiling down this enormous set into fundamental categories based on these negation symmetries.
So it simplifies the picture, focusing on the essential structure.
Exactly. You're removing the superficial differences caused by just, flipping bits here and there.
Okay, that makes sense from a logic or computer science perspective, finding the core functions. But let's loop back to the number theory students listening.
Yes.
This might still feel a bit abstract, maybe disconnected. Where's the bridge to number theory in counting these function types?
That's a really good question. The connection is in the method and the underlying concept. At its core, A000231 is a counting problem.
Okay.
We're counting mathematical objects, these equivalence classes of functions, under the action of a group, the complementing group.
Right, counting under symmetry.
Precisely. And counting problems that involve symmetry are absolutely everywhere in mathematics, including number theory. Think about counting distinct ways to color beads on a necklace when rotation is considered the same.
Yes, Burnside's lemma, polyenumeration, that sort of thing.
Exactly. Those tools, they come up in combinatorics, sure, but they have deep ties to number theoretic ideas involving, say, modular arithmetic, group structures, partitions maybe.
Okay, so it's not about the Boolean functions themselves being number theoretic objects, but the act of counting them modulo these symmetries uses mathematical principles common across fields.
That's a great way to put it. The framework is analogous. We're using group actions and symmetry to understand structure, whether it's the structure of integers, modulo $1, or permutations, or in this case, Boolean functions. And what's neat here is seeing how these simple negation symmetries create a much more manageable structure.
Yep.
The number of inequivalent functions, A000231, grows much, much slower than the total number 2 vocal hours.
Suggesting an underlying order.
Yes, an order revealed by symmetry. For a number theory student, it's a good reminder that tools like group theory aren't confined to one domain. They reveal fundamental properties, hidden structures across different mathematical landscapes.
That's a really insightful connection. It emphasizes how powerful these abstract mathematical tools are for finding order wherever you look. Thanks for clarifying that bridge. All right, so just to quickly recap for everyone, we've been talking about OEIS A000231.
Yep.
And this sequence counts the number of, let's say, fundamentally different Boolean functions with null inputs.
Where fundamentally different means you can't get from one to another just by flipping some input bits or flipping the final output bit.
Using that complementing group action we discussed.
Exactly. And this idea of equivalence helps make sense of the huge number of possible functions. We often think of Boolean functions via truth tables or maybe algebraic normal form.
Right.
But this equivalence groups them into essential categories based on these negation symmetries. It's a really useful simplification, especially, say, in logic design.
Okay, so thinking about that, here's something maybe for you, the listener, to mull over. How might the specific symmetries of one particular Boolean function which of those complementing operations leave it completely unchanged? How might that relate to the size of the equivalence class it belongs to?
That's getting into orbit stabilizer type ideas. Good question.
Yeah. Could looking at these classes tell us something deeper about the structure, maybe the complexity within that whole massive space of Boolean functions?
It's definitely a path to explore. And we encourage you to browse the OEIS more, look for other sequences related to counting things under symmetry. It pops up everywhere.
Absolutely. Understanding how to count distinct structures under symmetry is, well, it's just fundamental in math, and it has real implications, doesn't it? For designing algorithms, understanding complex systems.
Of sorts of areas. It's a core skill.
Well, thank you for joining us on this deep dive into A000231. We hope it sparks some thoughts about how different mathematical areas connect through ideas like counting and symmetry.
Thanks for having me.